So in this video we're going to go over some conservation of momentum and impulse problems that I've assigned my students in a regular non-advanced placement physics course. So these are going to be the solutions to those problems. And the first problem, we have a great horned owl swooping in to pick off a varmint. I don't state what kind of varmint it is, but I mean, you know what owls eat. So we give a mass and a velocity to the owl and a mass to the varmint. So the question is, what is the owl's speed just after it grabs the varmint as a result of this collision? And we're going to also calculate the impulse felt by the varmint. So I'm going to assume that, well, actually it's stated that everything's going to the right. So we have our givens, and we have the owl's initial velocity. I've denoted owl by a lowercase o and the varmint by lowercase v in subscripts. So, for example, this v sub oi is the initial velocity of the owl, and this v sub vi is the initial velocity of the varmint. I could have put commas in here, but I didn't bother this time. A lot of times I will, though, to make things a little bit more clear. So this is a classic type of conservation of momentum problem. Conservation of momentum is one of the deepest laws of nature. It's a result of the fact that there is nothing special about the laws of physics that differentiates left from right or anything like that, certainly not on the macroscopic scale. So the fact that that is true means that momentum is conserved, at least total momentum is conserved, between just before and just after an interaction. So what does that mean in this problem? Well, we start off with an owl and a varmint, and we end with an owl and a varmint. So we have two things on each side, so the momentum initial of the owl plus the initial momentum of the varmint must be the final momentum of the owl plus the final momentum of the varmint. That's literally just reading that equation from left to right. So every momentum is now substituted with mass times velocity for that object, except one of them. I actually plugged in 0 for the varmint because the varmint was initially assumed to be at rest. So now we're trying to find the final velocity of this system, because once the owl picks off the varmint, they're going at the same velocity. So I just substituted that v sub f in for each of these final velocities because, once they become one and the same, the owl's picking off the varmint, they're going at the same velocity, so I can just replace each of these with that same final velocity. That is helpful when we're doing the math because I can factor that term out. And now I can divide both sides by this annoying term that's multiplying the term I'm trying to find. And we have this result. And now we're ready to plug in numbers. By doing some of these little algebra steps, the result was that I don't have to plug in as many numbers, and it's significantly less likely that I'm going to make a calculator mistake when I do plug in the numbers. So upon doing this, we got that the final velocity of that varmint owl system is 13.9 meters per second. That is 13.9 meters per second toward the right. That's what this plus sign is indicating here. And if I was stating this in English, I would just say 13.9 meters per second toward the right. Now that is important because velocity is a vector. We were pretending that it's not in terms of these calculations, but technically this should be boldface, and this right here would be a plus 14.5 meters per second, and then that everything would end up coming out in the end in this case. So now we know the final velocity of the owl, and the varmint for that matter, because they're attached together. Notice that it's a little bit slower than the initial velocity of the owl. After all, the varmint was at rest, and therefore by picking up the varmint, this slowed down the owl, but not by much because the varmint's mass is much less than that of the owl. Now the next part of the question was asking to calculate the impulse felt by the varmint. Now you should know there are two equations for impulse. One of them is that impulse is equal to the force times the time interval over which the force acted. If it's a variable force, you need to take the area of under a curve. Another equation is that impulse is equal to the change in the object's momentum. So the question is, okay, what do we know here? Do we know anything that will allow us to calculate change in momentum? Do we know anything that would allow us to calculate a force and a time? Well, we're not given a force, and we're not given a time of collision. So that version of the equation's out. So we must use the change in momentum version of impulse. So J equals delta P. So J for the varmint is equal to delta P for the varmint. Well, what does change in something mean? That's change in momentum. Well, that means final minus initial. So delta P for the varmint is P final for the varmint minus P initial for the varmint. And again, every one of those P's is an MV. So now we're ready to, we can factor out that that mass of the varmint, and by MV I mean mass times velocity. And that's a little confusing because we're dealing with a varmint who's denoted by M subscript V for varmint. But we can factor out this M sub V and result in fewer terms in the calculation. And when we plug those numbers in, we get that the varmint felt an impulse of about plus 3.76 kilogram meters per second. That is 3.76 kilogram meters per second toward the right. So now let's turn our attention to a similar type of problem. In this case, we have two minions. I decided not to put in pictures of minions this time, but you know what minions look like. A yellow minion and a purple minion. And the purple minion, the evil purple minion, catches the yellow minion in a collision. So the question is, what is the speed of these minions when the purple minion catches the yellow minion? What's the impulse felt by the yellow one? Or sorry, by the purple one? What's the impulse felt by the yellow one? And calculate the force felt by each. Those are parts D and E. So this seems like a long problem. And it kind of is a long problem, but the good news is that there are only 3 real calculations in this problem, as you will soon see. So the purple minion we had being the more massive one, and since it's going to catch the yellow minion who's also moving to the right, that means the purple minion must be going to the right a little bit faster. So here we have our givens. Always start off with your givens. They can often help you figure out how to solve the problem. So we see a lot of masses and velocities. There's a collision here, so collision sounds like conservation of momentum is going to be relevant, and indeed, that's exactly what we start with. So again, a purple minion initially, and a yellow minion initially, and a purple and yellow minion finally as well. And again, every P plugs in an MV, and with appropriate subscripts. Now, again, just like in the last problem, the purple minion and the yellow minion have the same final velocity. We're just going to call that V sub F, and that's what we're going to substitute in each of these terms. And then we're going to factor it out, and now solve for V sub F. After all, since we could factor this out, V sub F is what we're trying to solve for, so we're going to divide by both sides by this annoying term that's multiplying my V sub F. So now we have an equation for the final velocity of the purple-yellow minion system. So we plug in our numbers, and upon doing that, we notice that our kilograms cancel. That's nice. They should. We should be left with meters per second. And we get a final velocity for that system of plus 2.79 meters per second. So the yellow and purple minions are both going toward the right at 2.79 meters per second. Again, quick reality check. Does this make sense? Well, just like in the owl problem where the owl was slowed down by colliding with the varmint, well, in this case, the purple minion is slowed down by colliding with the yellow minion. But the yellow minion, which was also going toward the right, whatever, ends up picking up speed as a result of this collision, because this collision occurred in the direction that the yellow minion was already traveling. So now we can turn our attention to calculating an impulse, in this case the impulse felt by the purple minion. Well, let's see, again we don't have a force, we don't have a time, so we're going to use impulse is change in momentum. Which change in momentum? The change in momentum for the purple minion, delta P sub P. So that'll be the purple minion's final momentum minus the purple minion's initial momentum. Well, we can get this because remember every P is an MV, and we know the masses and we know their the initial and final velocities. After all, we just calculated the last of those. So we factor out our mass. In this case, though, we're not going to divide both sides by anything because we're being asked for the impulse. So we're ready just to plug in numbers right now. And upon doing so, we get that the impulse felt by the purple minion is negative 11.5 kilogram meters per second. That is 11.5 kilogram meters per second toward the left. Notice those units. You can also call it 11.5 Newton seconds because a Newton second is also an impulse unit. It's the same thing as a kilogram meter per second. If you don't believe me, remember a Newton, well, it's a unit of force. Force equals mass times acceleration. So units of force must be units of mass times units of acceleration. That would be kilogram meters per square second. Well, kilogram times meter per square second times seconds is kilogram times meters per second. So that's how you can make sense of those units as well. What about the impulse felt by the yellow minion? Let's notice I rephrased this slightly. I didn't say calculate it, I said determine it, though in the original question it wasn't so clear. Well, Newton's third law tells us that every force results in an equal and opposite force. So the impulse felt by the yellow minion, which by the impulse equation is the force felt by the yellow minion times the time of the collision. Well, we can't calculate the force yet, we're getting there later, but since every force is an equal and opposite force, the force felt by the yellow minion as a result of colliding with the purple minion is equal to the negative force felt by the purple minion as the result of the collision with the yellow minion. Well, let's pull out that minus sign. We know the force felt by the purple minion as a result of the collision with the yellow minion. That's what we just calculated in part B. So, since the times for the collisions are, of course, the same, that means that the impulse felt by the yellow minion is the negative of the impulse felt by the purple minion. And I misspoke. I said that we calculated the force felt by the purple minion in part B. We calculated the impulse felt by the purple minion in part B. That's what we're going to plug in right here. And the result ends up being that the impulse is positive 11.5 kilogram meters per second. Unfortunately, I forgot to cut off my sig figs here, but it's plus 11.5 kilogram meters per second toward the right. That is the impulse felt by the yellow minion. Does that make sense? Well, you know impulse is change in momentum. The yellow minion ended up going faster than he was to begin with, so that must mean that he must have received a positive impulse. That is, one toward the right. So, all makes sense in this scenario. Now, what about the forces felt by the purple and yellow minion? Well, for part D, the force felt by the purple minion, well, we get that from the impulse momentum theorem. So the impulse momentum theorem tells us that that same thing, impulse, that is change in momentum, is also force times time, where in this case when we say time, we're talking about the time interval of the collision or the interaction. So J is delta P. But we also know that J is F delta T, impulse is force times time. So therefore that is equal to delta P. Well, we've already calculated delta P. That's really what we calculated in parts B and C. So now that we know the time of the collision, we can plug that in and get the force. And in doing so, we get that the purple minion feels a force of negative 141 newtons. That is, a force of 141 newtons toward the left. What about the yellow minion? Well, Newton's third law tells us about that. The force felt by the yellow minion is the negative of the force felt by the purple minion, so that would be 141 newtons toward the right. So that's how you deal with these types of situations. So next problem. We have purple and yellow minion again, and this time they collide and are moving together after the collision, but in this situation, the yellow minion is moving toward the left instead of toward the right. So similar situation as before, but this time it's a different collision. Now I made this slightly unrealistic because if you look back in the last problem, I made the time of collision pretty short. I should have made this time of collision much shorter, but instead I only made it a little bit shorter. But still, the fact that the time of collision is shorter should be expected because of the fact that we're talking about a very quick change in momentum for both, because of the fact that they're going opposite directions. That's why head-on collisions in vehicles are so deadly. So, same problem as last time, just with different numbers. So, we have our givens. Notice again the negative sign on the yellow minion's initial velocity, but otherwise it's the same problem. So, conservation of momentum, purple and yellow minions in, purple and yellow minions out. Every P is an MV with appropriate subscripts. And note that the final velocity of that system is the same, so we factor that out. So, again, we just replace each of these V finals by just one V final, and we factor it out and solve for it by dividing both sides by the total mass. And when you do that and plug in the numbers, you get that the final velocity of the system is plus 1.07 meters per second. Well, that's slower than it was before. That makes sense because the yellow minion's initial momentum was directly against the initial momentum of the purple minion. So that's going to result in a larger change in momentum for each of them. So the final speed is 1.07 meters per second. The direction is toward the right. And question is, does that make sense? Well, let's see. The purple minion is more massive and moving toward the right. The yellow minion is less massive and moving toward the left, but at a smaller speed than the purple minion. So given that, you would expect that if they collide and stick together, the purple minion with the obviously larger initial momentum, that is going to end up winning out. Now, if the yellow minion's initial velocity was larger and also moving toward the left, then whether they would end up moving toward the right or to the left would depend on exactly how large the yellow minion's initial velocity was, at least compared with the mass and the mass of the purple minion. But in this case, it should make sense that their final velocity would end up being toward the right, as indeed ended up happening. Now part B, the impulse felt by the purple minion, that's the same calculation as in problem 2 that we just did a few minutes ago. And same types of givens, same types of equations. Impulse is change in momentum. Change in momentum is final momentum minus initial momentum. In this case, it's for the purple minion, indicated by the P subscript, and final and initial being by F and I subscripts. And again, momentum is mass times velocity. In this case, it's the same mass, so I factored it out. Notice I'm not canceling it. I can't cancel it. There is no mass on the left side of the equation, but I can factor it out to save a little time in the calculations. And now, ready to plug in numbers. Notice I plugged in the non-rounded result. Of course, it's even farther than this in the calculator, but I gave more decimal places to indicate that it is a non-rounded result. And after all, we don't want to introduce any additional errors. And after doing this, we get that the impulse felt by the purple minion is negative 57.6 kilogram meters per second. If I go back to problem 2, you'll notice that this is a larger impulse than before. How about the impulse felt by the yellow minion? Well, Newton's third law comes to us again. Since every force results in an equal and opposite force, that means that the impulse felt by one is the negative of the impulse felt by the other in the two-body interaction. Again, J equals F delta T, and of course, delta T is the same for both of them. So, by Newton's third law, we just get the negative of what we got in part B. Positive 57.6 kilogram meters per second. That is, the yellow minion feels an impulse of 57.6 kilogram meters per second toward the right. What about those forces? Well, we expect a larger force than what we got before. Last time the force was something like 411 newtons. So in this case, we get a noticeably larger force, over 1770 newtons, and a minus sign indicating that it's toward the left. So the purple minion feels a force of 1770 newtons toward the left, whereas the yellow minion, by Newton's third law, should feel a force of 1770 newtons toward the right, because every force results in an equal and opposite force, the equal part being the fact that these magnitudes are the same, the opposite part being indicated by the minus sign, just like before, and the result is indeed what we expect. So, there it is. Now, what about a football game? In this case, the difference between this and the minion problems is that after the collision between the offensive and defensive players, they don't stick together. In this case, we're saying the defensive player is moving toward the right at a certain speed. So the question is, what's the velocity of the offensive player after the collision? What's the impulse felt by the offensive player? And what's the force? We didn't ask about it for the defensive player because, as we saw in problems 2 and 3, it's the same as the offensive player, just opposite direction. So, we have our givens, we have our masses, we have our initial velocities, and we have the one known final velocity. Question is, what's the other one? So, we set up, just like before, conservation of momentum. Sum of P initial equals sum of P final. We have 2 players in, 2 players out. I'm calling the offensive player number 1, the defensive player number 2. So, here's where we're at so far. And now, we plug stuff in. Every momentum is a mass times velocity. Now plugging in and well, first we're going to isolate. We're solving for the final the final velocity of the offensive player, and that's embedded in this term right here. Well, this term is multiplied by something, and that whole thing is also added to another term. So first we're going to subtract off that other term that's added, so subtracting m2 v2f from both sides of the equation and getting m1 v1f by itself. This is the result of that. And now we divide both sides of the equation by m1, and upon doing that, in fact, you can separate this fraction out if you wanted to and have v1 final equals v1 initial plus m2 over m1 times v2i minus v2f, the v2i minus v2f being in parentheses. But in this case, we're just going to plug in the numbers directly. The result of doing that is that the final velocity of the offensive player is negative 1.77 meters per second, that meaning that he's going 1.77 meters per second toward the left after this collision. Now, the impulse felt by the offensive player, well, impulse is change in momentum. We know the final and initial velocities and the mass of the offensive player, so that's enough to calculate a change in momentum. Impulse is delta p, but that's p final minus p initial, and I used the 1 subscript to denote, hey, this is the offensive player who we're calling number 1. And we can, again, factor out this mass 1 if we want, and then plug in our numbers. And upon doing that, we get that the impulse felt by the offensive player is 490 newton seconds toward the left. I could call this kilogram meters per second if I wanted to. The only reason I'm calling it newton seconds is because I noticed that part C is going to be asking me to do something that's going to result in canceling one of these units right here, so I'm just getting it ready already. So part C, calculating the force felt by the offensive player. We are told that the time of the collision is about 45 thousandths of a second. So the impulse is force times time. Now we're ready to use that equation. The fact that we have 2 different equations for impulse allows us to do a lot of things, because a lot of times you can only calculate impulse one way with early information, but then once you get later information, you can calculate something else after having already calculated the impulse. In this case, we can calculate the force now. So force is impulse divided by time. In fact, remember, since impulse is change in momentum, just writing the equation this way, this actually is directly Newton's second law. Force is equal to change in momentum divided by change in time. And that usually reduces to F equals ma in our problems, but not always. So that's something to keep in mind. But writing it this way is always true. Anyway, we already calculated the impulse. Divide by that time, and by change in time I'm talking about how long did the collision last, and of course that means that the best we're really doing here is calculating an average force, but that's good enough for this problem. So we get that the offensive player felt a force of negative 10,900 newtons. That's a lot of newtons. That's over 2,000 pounds of force. Fortunately, that player was only feeling that force for a very short time interval, but these are actually fairly realistic numbers. But you can see why collisions in football can potentially do so much damage, because you're dealing with very large forces. So now, another minion problem, and a similar situation as we had before with the football players. So minion Jerry is slowly walking toward the right, and the minion Tim is walking toward the right at a larger speed. And then they collide, and the result of this collision is that Jerry is sent toward the right at an even larger speed than what Tim was walking toward the right at. So you know how minions are. They like to do these types of things. So obviously Tim pushed Jerry with considerable force as he collided with him. So here we have our givens. And again, it's a conservation of momentum problem. And again, 2 minions in, 2 minions out. So we have Tim and Jerry, denoted by their respective subscripts. And it looks like I forgot to run an animation properly here. But in any case, after this, we have every P is an MV. And isolating for the term that has the final velocity that we're interested in calculating, we subtract an an mj vjf from both sides, because this term right here is that term that has that final velocity. And the next step, we're going to divide both sides by m sub t, the mass of Tim. And there we go. And plugging in the numbers, we end up getting that the final velocity of Tim is negative 0.35 meters per second. That is 0.35 meters per second toward the left. Now, in terms of the impulse and the time of the collision, for the impulse, we have the fact that impulse is the same thing as change in momentum. Well, and I have a little typo. This should say P sub ji, not J sub ji. So impulse on Jerry is equal to the change in momentum of Jerry, which is Jerry's final momentum minus Jerry's initial momentum. Again, this should say P sub ji, and that's equal to m sub j times v sub jf minus v sub ji. I've factored out the mass already there, but if you didn't see that, this term right here would be m sub j times v sub jf. This term right here, again, should say p sub ji. That would be m sub j times v sub ji. And the m sub j's that are in both terms factor out. So now you're ready to plug in the numbers. And upon doing so, you find that the impulse felt by Jerry was plus 73.6 Newton seconds. How long did that collision last? If the force was 445 newtons, by the way, that's 100 pounds. So if the force was that strong, given this change in momentum, this impulse, that collision must have lasted for about 1/6 of a second, 0.165 seconds. So now consider a quokka. I forgot to put an image of a quokka in this, but the quokka is the cutest animal in the world. You should just Google image quokka. And they're a type of wallaby that lives on an island off the coast of Australia. But they are furry, and if they are sliding on a rough surface, that is going to create some friction. So the question is, given that this friction has a certain force, how long will it take for the quokka to come to rest? And you are not allowed to use kinematics equations in this problem. In other words, no v squared equals v naught squared plus 2a delta x or anything like that. You have to use conservation of momentum and impulse here, in particular the impulse momentum theorem. Notice in my givens, the force is negative. If we're saying that the quokka is going toward the right, which is what I'm assuming here, then that means the force must be going toward the left, because friction is the bastard force. It's always acting against you. So it's acting against the direction of motion, at least between the two surfaces. So here's where we're using the impulse momentum theorem. Now, this is slightly different from how we stated it before. Before we stated it as J equals delta P. Well, this is exactly the same thing, because after all, delta P is P final minus P initial. So since J is P final minus P initial, that means that you can add P initial to both sides to say that J plus P initial is equal to P final. And that's just how we've written it right here. You can also think of this as a starting point. So just as back in the energy unit you had total initial energy plus work equals total final energy, well, here we have initial momentum plus impulse equals final momentum. In other words, what you end up with is equal to what you had to start with plus what you added to the system. And that is indeed what impulse is. It's momentum that has been added to the system by an external force, in this case, friction. And in this case, that, quote, adding is actually a subtraction. But that's going to show up soon. So every P is an MV, and we're saying that the quokka ends up coming to rest, so P final ends up being 0. And we're wondering what this time interval is. So we get F delta T, first off by itself, by subtracting MV initial from both sides. And now we divide both sides by F. Notice the minus sign here. Remember the force is negative, so these negatives are going to cancel out, giving us a positive time when we plug in our numbers. And indeed, we get a time of 0.959 seconds for that quokka to come to rest. So next, we have a chicken walking toward the right at 0.450 meters per second. A weasel impacts it from behind, providing a force of 8.5 newtons over a time of 1.4 seconds, until we assume that the weasel has made minced meat out of the chicken. So calculate the chicken's final velocity in this situation. Well, we know what weasels do with chickens and everything like that, but in this case we're assuming that the weasel has hit it from behind as opposed to grabbed it. But in any case, the force is what's being applied to the chicken, so it really doesn't matter whether the weasel has hit it or actually held onto it, because we're told the force that acts on the chicken and the time. So we have initial momentum plus impulse equals final momentum. Again, what you started off with plus the change is equal to what you end up with, because after all, impulse is change in momentum, delta p. Every p is an mv, and we're wondering about the chicken's final velocity, so we need to divide both sides by the mass, because this v sub f is what we're after. So upon doing that, there's the left-hand side of the equation divided by mass to get v final by itself, and separating out the terms, this mv over m is just a v, and we still have an ft over m. It doesn't cancel completely. So we plug in our numbers, and upon doing that, remembering that a newton is a kilogram times a meter per square second, so the kilograms cancel, meter per square second times seconds is meters per second, so the units here work out with the units here, and they add up. You get 3.46 meters per second. That is the chicken's final velocity, 3.46 meters per second toward the right. So now, one final problem involving these types of just general calculation concepts with conservation of momentum and everything. Going back to the typical basic conservation of momentum problem. You start off with a system and it shoots something or throws something or whatever, and there is a recoil velocity. So we have a cannon shooting a 25 kilogram cannonball toward the right at 225 meters per second. That's pretty fast. That's like 500 miles an hour. So we have our givens. The question is, what's the recoil velocity of the cannon? So conservation of momentum, just like before. The initial momentum and the final momentum, for that matter, are both zero, but the fact that we know that the total final momentum is zero allows us to calculate something involving the individual final momenta, which add together to give the total final momentum. So there's the total final momentum is the final momentum of the cannon plus the final momentum of the ball, and we're assuming that this 1525 kilogram mass did not include the mass of the cannonball. So every p is an mv. We're solving for the final velocity of the cannon, so we want this whole term first by itself, so we subtract this thing off. And now we divide both sides by the mass of the cannon, and now we plug in our numbers. And when we do that, we get that the final velocity of the cannon is 3.69 meters per second toward the left. So that's kind of the easiest type of conservation of momentum problem. So just kind of going full circle and coming back to this. So hopefully these problems were helpful, and certainly if you have any questions, please let me know. Thank you.